Okay, so hi everybody. Really happy to be here today to talk a little bit about Nova, about supernova actually. A really short, quick recap on Nova. We just had a wonderful presentation by Chi on Nova. So basically, the core idea of Nova is folding schemes that allow you to basically take multiple instances that are the same of a problem and combine them to, in the end, have a big polynomial that you can construct because the commitments you use are like Peterson commitments, so they are additively homomorphic. You use the Fiat-Shamir heuristic to have to sample random coefficients, and so you can combine them all, and basically then this is what we just saw. The challenge here is generated via the Fiat-Shamir heuristic. You can combine instances 1 and 2 and witnesses 1 and 2 into the final witness, the final instance. You have all of the problems with the cross term and the error term and the scala you have to add to make a relaxed R1CS instance. This is just what we just saw, so I'm not going to go through it all. And basically, in the end, you have this big chain of circuits. You can aggregate it, and at each time you have a commitment to the previous step, a commitment that's the running witness, which is the accumulator, and you can accumulate each new instance over the old ones. And at the end, you have a recursive proof that proves all of the steps at the same time. For instance, using polynomial commitments to do that. So one question you might ask yourself is, okay, we have Nova, that's cool. What good is it for? Are we just doing it for fun or because it's beautiful mathematically? Or do we actually want to prove things using this? And one really cool thing we could do is a VM, right? So obviously, doing a ZK EVM is very important because it would allow us to have really, really good scalability on Ethereum L1 and on maybe other L2s by building, I don't know, L3s. But you could also prove other computation like RISC-V, WASM. So let's try to use Nova to build a VM. So one approach that you could have is, okay, Nova can only fold similar instances, right? You have to have the same circuit all the time. But in your virtual machine, you have a number of instructions, right? If it's a RISC-V, you have a few instructions. If it's the EVM, you have all of the opcodes. And so how do you do that? Well, you have to have a similar circuit all the time. So you make a big circuit in which there is all of the instructions. And each time you are going to fold it over and over. And at each step, you are going to have an entry into the next step that tells you, okay, I want to use this part of the circuit for this instruction, or this part of the circuit for this instruction. So for instance, here you have a few opcodes. Now, this seems like a good approach maybe, but it's not that good of an approach because, well, there's a lot of opcodes in the EVM. Right now, there are 141. In virtually all virtual machines, there's a lot of instructions. You have to make a very, very big circuit. So the size of the universal circuit that contains all of the instructions is bigger than the size of all of the circuits combined. And so you end up with this really, really, really big circuit. And remember, in Nova, okay, you can fold them, but at the end, the prover work, the work of the prover, is still proportional to the size of the circuit. So this means the prover work is going to be proportional to this enormous circuit that contains all of the instructions. Oh my God, it's very bad, too much opcodes. We don't like this. So,
can I ask?
Yeah, of
Why
course.
is it bigger? Can't you factor parts of the code from different opcodes into a common circuit?
I guess you could do things like that. So maybe it's not maybe there are parts of them that you could actually factor, but you have cases like Ketchak, which is, I mean, it's really bad, it's really big. Maybe you can take parts of the other ones, but and remember, as it's an arithmetic circuit, you cannot as easily use parts of the code in other ways as you would do in normal code because it's acyclic, if I'm not mistaken. So I don't think it's that easy to factor things.
I think another reason because Nova only
Yeah, but in this case,
factor because everything has to be the same factor.
yes, but here we are we are imagining a big circuit in which everything is combined, and so
And that's why you can't factor it out.
yeah, like you have to have one big instance or one big circuit that contains everything. So, and you can't really, it's acyclic, so it's not easy to do that. So, as I just said, the proof of cost is proportional to the size of the circuit. The universal circuit, universal means there is all of the instructions inside. You cannot parallelize the proof. You have to run each step one after the other. And the prover memory requirement is also very big. Okay, so maybe you could think, okay, let's do an universal circuit with only a few small instructions. That would make it smaller, it's true, but it wouldn't be that good actually, because, well, you wouldn't have, for instance, the EVM, you would have to simulate it with fewer instructions. And also, as you have really small instructions, now you have to make billions of steps to make a small program. And actually, before, there was no better way to do that. So, for instance, you've got like papers by Elie Ben-Sasson, before he was even working on Starks, being like, oh, how can we do that? But before the EVM even existed, it was like to simulate traditional VMs. But there was no better solution. Enter Nova, Supernova even, which uses Nova. And so, what's the idea of Supernova? Okay, first I'm going, well, not to show you the ID, because here you don't see the core ID of Supernova. This is for a little bit later. But basically, I can already tell you the result. So, obviously, it's cheaper than a general ZK Snack prover. Okay, that's the goal. And also, the prover's cost per step is proportional to the size of the circuit of the executed instruction. So it's not proportional to the size of all of the instructions. We can basically pick the instruction we want so that the size does not explode. We just the cost of the prover is proportional only to the instructions it does. So
Sorry.
yeah.
You explain the extrusion arm.
Yeah.
So please, could you explain the execute instruction more precisely? Yeah.
The executed instruction. Okay, so imagine you are in the EVM, you have opcodes that are executing code. These are the instructions. Like in the context of the EVM, executed instruction just means executed opcode. If you are on a RISC-V, for instance, or WebAssembly, or WASM and everything, there are different opcodes. Just like in every processor or virtual machine, there are like instructions. I don't know if it's clear.
Okay, sure.
So why would it be very interesting? Well, the most interesting thing I think are ZK VMs. Okay, you can do other things, VDF, so like verifiable delay functions in which you can prove that it takes some time to compute. ZK bridges, like okay, you want always to validate on one chain you want to make a light client on one chain of another chain, and so you have to validate the consensus, and so it's going to be always the same. But you also have other ideas, like for instance for ZKML. Okay, so what's the core ID? The core ID is non-uniform IVC. So we just saw what IVC was with Nova. The idea of non-uniform IVC, and basically I'm going to show you an image that it's not here, it's just after, but that basically summarizes everything. The core ID basically can be summarized in one sentence, and I'm going to show you the end thing because you are going to get it. Instead of just the classical Nova circuit with the computation we are doing, which is F, and a verifier circuit, now we have an additional function which is called phi, and which is going to select the next instruction that is going to be used. And we are going to have a lot of running instances, actually one running instance per instruction, and each time we are going to fold the instruction we are doing on the running instance of this instruction. So basically it's just like if you had 141 Novas separately that are running in parallel. Okay, it's not completely 141 Novas running in parallel. It's just the instances that are running in parallel and being folded on one another. Actually, this thing, you only have one of it, one per step. And let's dive a little deeper to understand like how it works. So let's get back a little. Okay, so we will have L plus one non-deterministic functions. L is just the number of instructions. So for instance, in our case, it's 141. But it's L plus one because we have this one, which is phi, I guess. And phi, basically, it's going to be a special function that takes as input the outputs of the previous instruction and that chooses which instruction is the next one, right? So basically, it allows for the sequentiality of a virtual machine. Like, okay, you have one thing, and then you take the output of what's happening, like the state and everything, and you can get what is the next instruction, just like a stack in some way. And you have the initial input z. You are going to apply the circuit like each time, folding just like as Nova, but now the index of the next instruction, which is called J, you will see J a lot more after, is going to be the result of computing phi, which is the function that chooses the instruction over the witness and the previous outputs. Okay, so just to make a little side note, let's say we want to use supernova with only one instruction. Well, actually, we just get back to Nova. Like, this is exactly Nova. This is supernova with one instruction. So the phi function is basically always returning one. Like, okay, we always return the first instruction. There is no instruction 2. And so this is actually Nova. You've got here the computation, the function. We've got the verifier circuits. And each time, we just run always the same function. So this is just Nova. But here is the more important part, which is supernova. Okay, so basically supernova, at each step, is going to take all of those inputs. So the witness, that is like the input that often we want in private, that we are going to put. This is the output from the previous step that we are going to pass each time. It's called PCI, but it's not a good name. It should just be called J, because J I minus 1, because basically it's the index of the previous. It's the index of the previous instruction.
The PC name made from the CPU structure, so like the PC register.
Yeah, that's program counter. Yeah. It's also called J. In this image, we only have PC, but yeah, let's say PC. And we have all of the running claims. So for instance, here we would have like 141 opcodes, for instance. And then what's going to be happening, so first thing we are going to run, we take this, we put them into phi, and we have phi, and we have the index of the function we have to use. So the index of the opcode. Let's say this time it's a mul. Okay, we are going to do mul. Then we take the same inputs and we do mul, and we have this. So now we have this and this. Okay, so now we have just done the simple part, which is computing the right opcode or instructions. Okay, this was the simple part. The most complex part is folding the previous computation we did just before in the big square that you don't see here because you have to imagine it. Here we take this, which is just the return of the phi function, but from the last time. We put it into a multiplexer that is going to choose the right instance, right? We have the right one, for instance, it's mul. Okay, let's say mul is this one. We are going to verify that like the previous instance, we are going to fold the previous instance and verify that it has been done correctly using this also. And then we get an updated running claim with basically, again, all of the instructions that we can use for the next steps. Are there any questions here? Is it clear or?
What's PC used for?
So PC is the index of of the instruction in all of the instructions. So for instance, let's say it's the EVM, we have 141 instructions. If PC equals 2, it just means it's instruction 2. Let's say it's a multiplication. And this is what's computed by this function, which is basically what we add. You can see here, basically what Supernova is adding is everything that's in blue, right? Everything that's not in blue, it was already kind of in Nova, except the fact that there are multiple ones. Yes?
So the PC actually is the index of instruction, not the address of code address of in the code memory traditionally.
I think it's the index of the instruction, yes. They are just indexed.
Index of the different instructions. For example, we have 100 instructions.
No, it's indexed in the program. not
Index in the
code.
program.
Yeah. So
Then we must have a mapping from the address of instruction into the type of instruction, right? Whether if the program counter is the traditional program counter, so it's just the address of the instruction, right? It's
Yeah.
not the index of instruction in the ISA, right?
Yeah, so I guess like in this context, PC is just a number between, let's say, 1 and yes. And then of course, when you are running all of this computation, you have a mapping from, let's say, 2 to the address of the real like opcode that does the multiplication, for instance, if it's mul opcode.
I think probably
guess.
it's called instruction selector instead of
Yeah, it's instruction selector.
Make more
yeah.
sense.
So
Yeah.
that PC is for the identity of each executor, right? For each execution, right?
Sorry.
The identity of execution.
Yes, it's the
So
identity of
OP code, right?
yes, because
Okay.
let's say phi does not give like 2, but it gives 3. Oh my god, this whole block is going to change. We are not going to compute opcode mul. We are going to compute opcode add. I don't think that's the real order 2, 3 in EVM, but you know what I mean. And so basically, by doing this, we have multiple instances and we aggregate them. Okay, so now you might say, so you have 141 instances. Does that mean that the verifier is going to have to check them all? And okay, what about ZK? So those are valid questions. Just like in Nova, we have a pretty simple solution. We just wrap everything into a snark. So they use Spartan, just like in Nova, in this paper. But actually, you can use other snarks to do this, and it makes the end proof succinct, which is quite good. And it also makes the burden of checking all of the instances of all of the different instructions really simpler and succinct. As you can see, it's quite similar to Nova in some ways. The most important thing is basically just an add-on on Nova to make VMs. The most important thing is that you have a à la carte cost profile, which is a very beautiful French expression, which means you can choose like whatever the instruction you want, and you don't have to pay for the whole set of instructions. And of course, you've got a bit of recursion overhead, which is always the case with Nova. It's the cost of the verifier circuit, but it's mitigated if each instruction performs enough work, which is at least 10,000 gates, because obviously if you have very small gates, the recursion of the verifier circuit is going to to be too much and to make the whole thing more burdensome. But if, let's say, each instruction is very big, it's going to be way better to have this little verifier that's like 10,000 or 20,000 gates. And so for a summary, basically you only pay for what is executed. It uses folding schemes. You can put it in a big snark, and it's probably quite a good it's probably quite an interesting idea to make VMs and other similar like things. And just after that, there was Hypernova, which is basically extending this again by constructing again a kind of superset of what's possible with Nova and with Supernova by using a customizable constraint system, which is a kind of superset of R1CS and ARR and other constraint systems to allow for like a lot more possibilities. This is it. Thank you very much.
I want to know how that file works. How to decide which instruction?
Oh my god. How does this file work? Well, I guess that in a virtual machine like that, so they don't really specify it in the paper that much, but I guess in the virtual machine, if you have like maybe the state as an input and you know all of the previous instructions, you know the next instruction you want to use, right? So I guess it like it's known by the prover. I don't know precisely how it works, to be honest. Yeah, they pass it as input, but it's still a function, right? Like, I guess in the end, it's part of the public input that the verifier can see when it checks the proof that like the right instructions were chosen. I guess.
Maybe it's quite simple because you compile a program into a bytecode, you put into some that kind of instructions and just read that and to do a filter and output a PC.
Yeah, maybe phi is just a kind of big list that's pre-computed. I'm not sure about that, but maybe it could just be a kind of big list that's pre-computed with each inputs that is just deterministically giving an output, like an index for the next instruction. Because the prover, he knows what the program is going to be, so he can pre-compute all of this. But it's still called phi because you know it's a function. You have to verify it next in the circuit for the next step to fold it and everything.
And it's public, right?
It's what?
Phi is public.
I think it's public in the sense that the verifier has to know, like that the right instructions were selected. So I guess. Oh yeah, it's a sub-circuit. Okay, yeah. So the circuit, yeah, is public. Yeah, it's part of the circuit. Yeah, just like every instruction. Yeah. Okay, I didn't see it like that. Yeah. Any other questions? Does anybody want to build a next generation EVM, ZK EVM?
Good idea.
A2?